Given an array of A of 0 and 1s, we may change up k values from 0 to 1. Return the length of the longest contiguous subarray that contains only ones. Okay. Okay, so basically the phrasing is a little awkward, so I just want to make sure I understand it, especially since I have some reading comprehension issues today. Cool. Okay, so that's kind of interesting. The question is, yeah, I mean, I think the question reads very easily. It's just given an array, you could change x of them to ones. What is the longest subarray after that? And let's look at the constraints first. And k can actually be the entire array if they want to. A sub I is equal to 0, 1. Okay. I think my first reaction is kind of in general with these things is you know it is very common. Your intuition is to want to do it in a greedy way, and my first kind of reaction to that is like, well, if can we do it in a greedy way? Can we justify it or slash proof that we can do it in a greedy way, right? And if not, then what it is, how can we do it, right? Okay, cool. So I mean, I think there's a couple of n square algorithms. I'm just trying to think if we can do better. So the n square algorithm I would have is kind of just keep a partial sum. Basically, you could think about for every I from 0 to n, basically just and then for every j from also 0 to n or whatever, and then between those two things, how many k's do you need, right? Or yeah, between those things, can you create a contiguous subarray that contains only one, changing up to k values, right? And you can, and if we don't, and the very naive way of doing that is actually n cubed, but you could do some pre-processing such that, you can do it in n square, and maybe that's good enough. Well, for 20,000, n square is probably enough. What's that, 4 million? 40 million? 400 million? And I think you could even do better than that. You could actually add a binary section such that you could ask the question of, well, for starting from element I, instead of from I to j, you ask, well, is there a contiguous subarray from I to, I don't know, from I to I plus n over 2, and then is there, and then let me maybe write it down so it's easier to remember. So for example, let me kind of recap what I've been saying, which is okay. So the first naive way is something like for I is equal to j 0 to n, for j is equal to I plus I to n, and then is there a contiguous, terrible spelling, is there a contiguous answer from I to j, right? And if so, then you just take the max over I and j, and then that's your answer. When we're taking account case, and then so this is n square. Well, this is n cubed if you do this in a kind of naive way, but you could actually pre-process it such that you can answer this in O1, which maybe I'll show in a little bit. So this goes to n square, and since n can be 20,000, 400 million maybe is fast enough. Okay, well, I'm going to try to do that. maybe just because it's easier to code. But you can actually reword that just slightly, so that from 0 to n, binary search k such that maybe j. You could, yeah, j from I to n such that, well, we still have the same question, right? You have the same question here, except for instead of doing from from I to n, you could binary search this, right? Yeah, because this is a monotonically increasing function, or well, it's a Boolean function, but it's going to be, or it only changes state at one place, and what that means is that it's always going to be true. Well, I guess it could start with false, but it's going to be true, 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 true. At some point, it's going to be false, and then everything after that is false, right? So in that case, you could binary search j, and this is obviously of n log n time, right? And so I think I'm going to do that. I mean, I think n log n is fast enough, but I'm not going to lie. I'm going to do lazy first, and I'm going to do the n square way first. Cool. And then see what happens, I guess. If it's not fast enough, I'll just write the other way. And I accept the Holy Spirit. Maybe something like this. Well, because maybe I will actually phrase this as 0 and then j plus I. Okay. So then the question is like, well, with a to j, and oh yeah, the stuff that I forgot or didn't forget, just didn't do yet, is pre-processing the array, and you can kind of get yeah, and you can pre-process the array by just in this case, because it's from 0, the values are just 0 and 1, you could actually just do a running sum of all the numbers in an array, in a pre-calculated array, such that that let's say between these 5 elements, well, if the sum is 5, and you know that the 5 the index difference is 5, then that means they're all ones, right? And in that way, you can also use take account k if it's less as the number that you can fill. Meaning, if, well, like for example, if this actually corresponds to this array, and this actually sums to only 3, but 3 plus k that is 3, that means you can fill them, and that means that you can actually make a contiguous array out of them. Cool. So I'm going to just create an array now. I had issues with it off by one earlier, but and this is probably good enough to create on the stack. But yeah, okay, fine. I'll just create it on the heap. There's an off by one here somewhere, but well, maybe it isn't necessary. A sub. Wait, what? Oh, wait, now that, okay. Okay, cool. And then with this, we can answer queries in constant time. So now if, and I have to be careful about off by ones, but sum of plus j maybe this is equal to actually. It's if it's more than less than k, then this is a good match, and then I should do some max. No. What is the return wire? Oh, the length. So yeah, so and j is the length in this case. So something like that. Welp. Oh yeah. Oops. Cool. Yeah, then we've been off by one, but I think that's okay. Man. Well, let's actually get back to the basics. I feel like I this should be 0 somewhere. Maybe. Yeah. Still the wrong answer though, but that's fine. Okay. So 1, 2, 3, 3, 3, 3, 4, 5, 6, 7, and then 7. Okay. So the sum array is okay. Which? Oh, oops. Try to save. It isn't off by one here. Okay, so the number that we're probably looking for is 1, 2, 3, 4, 5, all the way to the end. So that's so 5 plus 6 is only 4. Oh. But that should be 10 is a... Oh, 4 is less than k. Okay. Oh, okay, that's fine. Wait, so k is 2. So, okay, so this form is wrong, but that's... What is the right one? Okay, so k is the number that we can replace, so it's actually k plus... okay. So this is the number that we have. And what we want is actually j. So something like this, actually. Okay. Oh, so that was just actually just really, really well. But somehow it came close enough. Oh man, that's just funky. Okay, so this is the number of things. 4 plus. Oh, no, sorry. Whoops. In the wrong direction now. Okay. There's some normalcy. But yeah. So yeah, I mean, I asked the question in an awkward way, and I think I just kind of shortcut it a little bit. But basically, this this part of the formula should tell me how many ones that are inside from I to I plus j, and you add k because that's the in order for the entire sub array to be all ones, it has to be at least j, right? And you use k to kind of fill that in. That seems okay, but I think the only thing that I have issues now is maybe the runtime. So so let's see what happens when we have, was it 20,000 elements? How many elements are? Well, let's try this one first, actually. The second answer before I get too confident. Or second test question. Okay, so that, at least for now, looks okay. What is the A size on this? So it's 19 elements. Okay. Just gonna, okay. No, not K, A size. Okay, and then now I'm just gonna, I'm just doing a lot of pasting. Okay, I mean, I know this is not 20,000, but we'll see what the number is. Okay, 3,000. Still wanting pretty quickly, but this, but this is like quadratic, right? So like, doubling means it wants 4 times as slow, but okay, maybe this is cutting it close, but all right, well, okay, well, 1 second. Okay, well, I'm I'm a little lazy, so I'm just gonna try to submit it. But once I have time, I'll do the optimization that we talked about with instead of J kind of looping over the entire A size. Okay, fine. Not gonna lie, I'm just, I think if I was an interview and I'm trying to be responsible, I definitely would have tried to do it right the first time. But I was just a little bit lazy, and clearly, yeah. I mean, I guess the time is over multiple test cases. But yeah, but noticing that this function it's kind of monotonically changing, and what that means is that this will start off being true vaguely. I mean, maybe it just starts off being false, and then but if it starts off being false, it'll always be false, or it starts off being true up to a point, and then it becomes false, and then it always be false after that, right? So what that means is what we want is kind of binary search from j from 0 to j plus I is less than or equal to size, which you could do some easy math, right? So you actually want to binary search this case from 0 to A size minus 1, which I guess I'm going to have to do now because if I want to solve it. I was half kind of certain that it wasn't going to work, but to be frank, I was just lazy, so. But give me a chance to binary search, or write the binary search. Let me just do, I always forget what variables I use, because sometimes, so head is equal to 0, tail is equal to, say, size minus I. So there are numerous ways you can write binary search. I'm not saying my way is cleaner or just right or the way to do it. Definitely practice it up. The way that I'm writing this now is probably maybe not to be honest, not super kind of friendly for interviews, but it's just how I've always been doing when I practiced doing competitive programming back in the day, and because that is guaranteed to be right, even though it is not perfect in the sense of like it doesn't do the minimal amount of operations, but it is correct. It does like a couple more, and you'll see why I'm talking like that in a second. But I'm just going to do some constant is equal to 10. Yeah, something like that. And what this means is that if, yeah, this may actually, you know, what was I going to say? This may actually become degenerate into n squared for small n's, is what I was going to say. So j is equal to 2, and we can move this up here. Oop. No, that's not, well, okay, well, it's half true. Something like that. So this is the case. Oop. Let's take that. Oh, what did I do? So yeah, if this is the case, then we know that, so if this is true, that means you want more, so you want to move the head to the mid. Okay, head is equal to j. Else, tail is equal to j. Okay, and now what I usually do is just I do head. Oh, I guess I just don't initiate, but yeah, okay. So now you know that this precondition is true, which is head plus 10 is less than tail. So, okay, fine. Actually, I'll use j just to kind of, oh, I guess I shouldn't have deleted this chunk because now I'm writing it the same way. But, might have to kind of check the bounds on this one, but it should be roughly right. No, I mean, it should be okay. I think this is okay. And yeah, and okay. Well, let's run this code again. Forget what it was, but it was like close to a second, right? And now it takes 4 milliseconds. So for a 19 element entry, so this is actually easier than so maybe I was just, like I said, I was really lazy. But cool. So yeah, that, wow, it's faster than 6%, so everyone hates me. But okay, fine. Yeah, so I think I actually like this problem. I think there's some pre-processing, which I'm a fan of. It's just another way to kind of think of the problem. Let me kind of restart this. But yeah, it's an interviewee. Yeah, I mean, it's a very straightforward-ish question. There's a very linear progression from how I read the problem and then slowly, like incrementally make improvements on it, right? And as an interviewee, that's all you can hope for. There's nothing like gotcha about it. All the components are kind of like, like if you take an intro algorithm course, you would know. So like binary search, I mean, maybe you haven't practiced enough, but you know what a binary search is. So I think that's pretty cool. So I think this is a nice-ish problem. As an interviewer, I also like this problem for the same reason, which is that it takes two, yeah, I guess just two, but a couple of first like very elemental pieces and put them together and ask the interviewee to solve it in a way that he or she maybe not seen before, but even if they have, you could kind of, well, maybe if they have, that's just a little tricky, but in general, they have seen it, then it is what it is. But if they haven't seen before, then you can kind of work through them, there's a linear progression on how to solve it slightly better, and that's, because we start with an n cube solution, we got it down to n square is still a little slow, we got it to n log n, right? And that's kind of all you can kind of, and if they show that down progression and kind of, and in every step of the way, as an interviewer, you're trying to, learn a little bit more about your candidate, and you would kind of push him or her in that direction. If like, well, and also if you give them one hint, is it enough, right? Like if you gave them, the pre-calculation hint, is it enough for them to kind of go from n square to n log n? So for that reason, I really like this problem. I could see myself giving it as an interviewer and kind of, play around with it maybe. I think in terms of difficulty, yeah, I think the only piece that I may be a little bit trickier is that the pre-calculation piece may be a little bit gotcha-y. Like if you've seen it before, it's something that you would just jump to. If not, maybe it's a little trickier to think about, and maybe you could give a hint. But it's still it'll be fascinating to kind of see how they work through the problem and into uh, um, yeah, so I think I like this farm a lot as an interviewer, and I would maybe add it to my arsenal. I need to maybe figure a way to take notes so I could actually use this in the future when I give interviews. But yeah, but that's fine. Cool.